Welcome to This Explainer. Today, we're diving into one of the most famous, powerful, and honestly, kind of mysterious forces in the entire universe, gravity. By the time we're done here, I promise you're going to look at the world around you in a totally different way.
Think about it for a second. Every single time you jump up, you come right back down, right? Drop a ball and bam, it hits the floor. It seems so incredibly simple, just a basic fact of life. But here's the crazy part. Nobody fully understands exactly why this happens. Not even the smartest scientists on Earth. To figure out why it's such a massive mystery, we first need to look at what we actually do know.
So, let's break it down simply. Gravity is an invisible force of attraction between any two objects that have mass. Basically, if it's made of stuff, it has gravity. Now, what's really mind-blowing about this is what it means for you. Right now, sitting exactly where you are literally pulling the Earth towards you. And the Earth is pulling you right back. It's totally a two-way street. But, why don't you see the ground flying up to smack your shoes? Well, because the Earth is just way, way more massive than you are. Since it's so huge, you move toward it, not the other way around. This whole mind-boggling idea was first really pieced together by a scientist named Isaac Newton, way back in 1687. You've probably heard the legendary story, right? He was sitting under a tree, saw an apple fall to the ground, and instead of just eating it like most of us would, he asked a question that literally changed science forever. He asked, what force is pulling it down? Why didn't it go up? Or, I don't know, sideways?
Now, Newton didn't just ask the question, he actually did the complex math to prove it. But hey, we don't need super complicated equations to understand what he found. The crucial point is that the strength of gravity comes down to just two very simple things, mass and distance. In plain English, if you have big, heavy objects that are super close together, you get really strong gravity. But if you have small, light objects that are super far apart, you get weak gravity. That is literally the secret recipe behind Newton's big discovery.
And this brilliantly shows how gravity completely changes depending on where you are in space. Let's take our moon, for example. The moon is way smaller and way less massive than Earth, so its gravity is only about 1/6 as strong. That means if you weigh 150 pounds right now on Earth, you'd only weigh 25 pounds on the moon. You'd feel incredibly light. In fact, you could jump 6 times higher than you can right now. How cool is that?
But wait, the moon's gravity doesn't just affect astronauts hopping around in spacesuits. Even though it's hundreds of thousands of miles away, the moon's gravitational pull is literally reaching right across the emptiness of space and grabbing onto Earth's oceans. It pulls the water toward it. That invisible long-distance pull is exactly what creates the high and low tides at the beach every single day.
The plot twist: Einstein's general relativity. For over 200 years, everyone thought Newton had it completely figured out. But then in 1915, Albert Einstein stepped up and totally changed the game. Einstein gave us a completely new way to picture the universe, a theory called general relativity. I want you to imagine that space and time are woven together like a giant, stretchy rubber sheet. Got that picture in your head? Now, if you place a super heavy bowling ball, let's say that represents the sun, right in the middle of that sheet, what happens? It creates a deep dip, a big curve in the rubber. Einstein said that dip right there, that is gravity. The Earth isn't being magically pulled by the sun like it's on a string. It's simply a smaller marble rolling naturally along the curved path that the sun created in the fabric of space.
Now, to prove this wasn't just some crazy magic trick, Einstein came up with a brilliant thought experiment to explain what he called the equivalence principle. Let's use our imaginations again for a second. Picture yourself standing inside an elevator, way, way up in a super tall skyscraper. Suddenly, a supervillain comes along and snips the wire holding the elevator, and you start free-falling down the shaft. What actually happens to you inside?
Well, if that wire gets cut, the elevator falls down, sure, but you fall at the exact same speed. Because you are falling together, you could completely float inside that elevator. If you let go of an apple in your hand, it wouldn't drop to the floor, it would just hover right there next to your face. For you, inside that falling box, it feels exactly the same as being an astronaut floating in zero-gravity space. Einstein realized something massive here. Free-falling in gravity and floating in empty space are effectively the exact same thing.
And this only works because of something truly weird about gravity. It's completely matter-blind. Actually, long before Einstein, Galileo proved this by dropping things off a tower. If you drop a 1-pound ball and a 2-pound ball at the exact same time, you'd probably think the heavier one falls faster, right? Nope, they hit the ground at the exact same fraction of a second. Gravity accelerates everything equally no matter how big or small, heavy or light it is.
Want to hear a super cool, kind of crazy result of this?
Imagine we dug a perfectly smooth tunnel all the way from one side of the Earth straight through the center, popping out on the other side. If you dropped a feather, a bowling ball, and a literal school bus into that hole, they would all fall together, perfectly side by side, and they would all reach the exact opposite side of the Earth in exactly 42 minutes. Every single time.
Real-world proof. How do we actually know Einstein was right? I mean, a stretchy universe sounds like a fun sci-fi movie, but scientists needed hard proof.
The very first massive test of this came in 1919 during a total solar eclipse. Think about it. If space is really curved like a dip in a rubber sheet, then a beam of light traveling from a distant star should literally bend when it passes near the sun's heavy dip. During the eclipse, when the sun's blinding light was totally blocked by the moon, scientists measured the positions of the stars behind it. And guess what? The starlight was bent by the exact amount Einstein predicted. Boom, he became world famous overnight.
But the proof didn't stop there, not even close. For the longest time, astronomers had this huge, annoying problem. The planet Mercury's orbit was wobbling, or precessing, around the sun, kind of like a spinning top that's just about to tip over. Newton's old math simply couldn't explain it. It was driving scientists absolutely crazy. But when they applied Einstein's new rules of curved spacetime to Mercury, the math worked out flawlessly. It perfectly predicted Mercury's exact wobbly path.
Now, if you're sitting there thinking this is all just weird, distant space stuff, think again. Einstein's theory is literally in your pocket right now. Seriously. GPS satellites orbiting Earth are further away from the Earth's center, right? So they sit in slightly weaker gravity. Because of the way curved spacetime works, time actually moves slightly faster for those satellites than it does for us down here on the ground. If scientists didn't use Einstein's math to constantly tweak and adjust the clocks on those satellites, the map apps on your phone would be off by kilometers every single day. You would literally never find your way anywhere.
As our telescopes get better and better, we keep seeing Einstein's math everywhere we look. Take a look at this wild phenomenon called a gravitational lens. Sometimes an entire galaxy is so incredibly massive that it bends the fabric of space so deeply it acts like a giant cosmic magnifying glass. It takes the light from a single star sitting way behind it, bends it around the sides, and tricks our eyes into seeing 4 or 5 duplicate images of the exact same star. Mind-blowing, right?
And then, of course, there is the absolute terrifying extreme of gravity, black holes. Remember that rubber sheet analogy we talked about? Well, a black hole is what happens when you put something so unbelievably heavy and dense onto the sheet that it essentially punches a bottomless pit straight into spacetime. The curve is so insanely steep and the gravity is so strong that absolutely nothing, not even light traveling at 1 billion kilometers per hour, is fast enough to climb out.
So with all this power, why is gravity the ultimate boss of the universe? Well, here is a totally wild fact. Gravity is actually the weakest force in nature. Yeah, you heard me right. The electromagnetic force, the stuff that powers your TV and makes magnets stick to your fridge, is trillions of times stronger. But here's the catch. Electromagnetism has positive and negative charges that constantly cancel each other out. Planets and stars are electrically neutral. But gravity, it has no negative charge. It only attracts. It never, ever cancels out. So across the massive, sweeping distances of space, gravity is basically the only player left on the field, completely dominating how the universe is shaped.
Which brings us to the final part of our explainer, the big unsolved mystery. What is space-time really? We've got the math, we've got the rubber sheet analogy, but now we're arriving at the most fascinating part of this whole journey.
I gotta admit something to you guys. Even after all the brilliant work by Newton and Einstein, modern physicists are still completely stumped. We know incredibly well how gravity works. I mean, we can land rovers on Mars and predict solar eclipses perfectly down to the minute, but we still don't really know why it exists. Einstein said mass curves space-time. Okay, but what exactly is space-time actually made of? Why does a chunk of matter just inherently know how to bend the universe around it?
This totally unexplained mystery leads us to the ultimate quest in science right now. See, we basically have 2 amazing rulebooks for the universe. General relativity perfectly describes really big things, like stars and planets, and quantum mechanics perfectly describes really tiny things, like atoms and electrons. The problem? When scientists try to jam these 2 rulebooks together to explain something like the center of a black hole, which is both supermassive and incredibly tiny, the math completely breaks down. The 2 theories absolutely refuse to play nicely and work together, yet. Which leaves us with the ultimate question. The story of gravity is definitely not finished. From an apple falling from a tree in Newton's garden, to giant planets rolling through a curved universe, all the way to the terrifying edge of a black hole, we've learned so much. But the final chapter? It's still completely unwritten. Somebody out there is going to have to find the missing puzzle piece that finally combines the big, the tiny, and the heavy into one grand theory of everything. So could it be you? Will you be the one to finally solve the mystery of quantum gravity? Keep asking questions, keep looking up, and who knows, maybe the next major breakthrough will come from you. Thanks for joining me on this explainer.